We have started this course by defining a planning problem, and then I have spent quite some time describing some algorithms for solving this planning problem. But you should now understand that the planning problem could have been defined quite differently. And this is because we've made quite a number of simplifying assumptions in our original definition. Dropping these assumptions would lead to different problems, which would require different algorithms to generate solutions. Now we're going to briefly look at another issue that we've ignored so far, namely that actions need resources. And in fact, time can also be seen as a resource. The approach that deals with planning with resources is known as scheduling. Scheduling is a field that is really much larger than artificial intelligence planning, with lots of sub-problems and lots of algorithms to solve these problems. So what I'm going to do here is only briefly talk about different types of resources there are, and then talk about how planning and scheduling can be integrated. Scheduling deals with the problem of assigning resources to actions. This assumes that we've already decided which actions we want to execute, so it assumes that the planning process as we've described it so far has been done. Now, the first question I need to answer is, what is a resource? And we can informally describe a resource as an entity needed to perform an action. This can be any type of entity. And one way to integrate this into our planning formalism would be to extend the operator definitions by adding more parameters that describe the resources that we need to execute instances of this operator. The parameters of an operator are of course described by variables. But not every parameter describes a resource. In fact, we can distinguish state variables and resource variables that are parameters to an action. State variables are usually those that are modified by an action in some absolute way. For example, if we look at our move operator that moves the robot R from location L to location L', that modifies the location where the robot is in an absolute way. We have the old location and the new location. So the location that is modified by the move operator would be a state variable. If we also wanted to model the fact that the robot consumes fuel while it is moving, we would use a resource variable to do that. And our modified operator description would then say that moving the robot from location L to L' uses a given amount of fuel. This would modify the overall amount of fuel available to the robot in some relative way, and that's why this would be a resource variable. Now, there are a number of different resource types that we can distinguish, and often the algorithm for solving scheduling problems is associated with a given resource type. The most common distinction we often see is of reusable versus consumable resources. Reusable resources are, as the name suggests, reusable, so they are available to another action after one action has completed. This could be, for example, a truck that we use to transport something from one location to another. After the transporting is done, the truck is available to another action. Consumable resources, on the other hand, are used up by the action. An example of that would be the fuel used by the robot. Another important distinction, especially from an algorithmic point of view, is whether our resources are discrete or continuous. Discrete resources usually come in a countable number of units. So for example, the cranes that we had available in the Dogworker robot domain, or if we have screws and bolts that we use in our domain. Continuous resources usually have a real valued amount, so that would be something like bandwidth or electricity that our actions consume. Another important special case are unary resources. These are resources where we have exactly only one available. Unary resources are particularly interesting when the resource is not shareable, because in that case, only one action that needs this unary resource can be executed at a time. If resources are shareable, the problem usually becomes easier, but there's usually some kind of capacity constraint on the shareable resource. An example of a shareable resource would be a generator that generates electricity for us. Another complication is that resources can have states. For example, if we have a generator that can produce different voltages as output, but only one voltage at a time, that means it is in a specific state producing a specific output. Now, all the actions that need the resource in that state can use it in parallel, but actions that need it in a different state can't use it at the same time. So, as you can see, there are many different types of resources that we may have to use. And often we require a combination of resources to execute an action. And all this has to be taken into account by a scheduling algorithm that assigns resources to actions. One way to look at planning and scheduling together is that we decide to first solve the planning problem. Then what we can do, given this action sequence that it produces as output, is we can assign time points to the beginning and end of each action. And then finally we could say we go from there to the resources and assign resources to the actions at given times. But this may not be a very clever approach. For example, if we are given a deadline, then first choosing an action sequence and assigning time to the actions in it may lead to inconsistent plans that we want to rule out at the planning stage. So we have a feedback from time to the planning itself. Similarly, the planning is influenced by the resources and vice versa. If we don't have the resources for certain actions available, then there's no point in including them in our plan. And of course, time and resources also interact, especially when we have things like shareable resources with a limited capacity or unary resources. So what I'm trying to say here is these problems really interfere with each other. And an optimal approach is probably one that interleaves the working on the different types of problems we see here as part of the solution generation process. So such a process would work on action selection, timing these actions, and assigning resources to these actions at the same time.